In this video, we're taking a look at the 2024 AP Physics 1 exam, question number 2 of our FRQ section, which is the experimental design one, which has a lot of different parts. Some of them are a little tough. Overall, I don't think it was too bad. So let's go ahead and read what we got here. So a student hangs a spring of unknown spring constant K vertically by attaching one end to the stand as shown in figure 1. And we only have a variety of cylinders of unknown masses, a stopwatch, and a digital scale. Okay, so we don't have every single thing we need, so we have to be conscious about the things they provided. And then design an experimental procedure the student could use to determine the spring's constant K of the spring. So we're looking for a procedure, and we want to have enough detail so another student could replicate the experiment. And then we want some steps necessary to reduce experimental uncertainty. So based on the things they gave us for the stopwatch, we're going to be looking for the period, the amount of time it takes to complete a cycle. So like start from the bottom, go all the way to the top, and then back down to the bottom. And then we have the symbol M, the mass of the cylinders. So here's what I'm going to do. This is probably not the perfect procedure, but I think it's pretty decent and then covers most of our bases. So we're going to measure and record the mass of each cylinder using the digital scale, hang a mass from the spring, allow it to hang at rest, pull the mass down, and then because we don't have any measurement tools like a ruler or a meter stick, I said about 3 centimeters the width of your thumb because I'm kind of pretending like I'm speaking to a student. And then release it. After 1 or 2 up and down cycles, hit start on the stopwatch at the lowest position and then hit stop after it's returned to that position 5 times. So I want to make sure it's 1 full cycle, which is the bottom all the way back to the bottom again. Divide your time by 5 and then record that as your T, your period, and repeat steps 1 through 5 for each mass. So I don't know if that's the perfect procedure or not, but that seems pretty decent to me. I may have forgotten some minor details, but that seems to be the gist of it. All right, now we want to indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. So we have to be thinking about the formula period of a spring equals 2 pi times the square root of m over k. In that case, if I see m over k, then I'm thinking the delta y over the delta x. So I'm going to want to put the vertical mass of m mass on the vertical axis and then the time squared on the horizontal. Because when I do some algebraic rearranging, I square everything, and then I have k equals 4 pi squared, and then I have m over t squared. So I'm going to want mass for my y-axis and t squared for my x-axis. And then I just basically explained it here. I said if you rearrange the period of the spring equation, then the product of 4 pi squared and m over t squared is k. So if you take the slope of m versus t squared, then you would find the value of m over t squared to be multiplied by 4 pi squared to get k. You can also switch what's on each of these axes, but then you would have to do 4 pi squared divided by your slope, and that would actually give you the same exact answer. So I'm guessing there's going to be multiple ways you can get the same answer. That's just the thing that came to me most naturally. Now we are continuing the experimental part of it, but it's going to be a different scenario, clearly. So we have a cart that is at rest. It's pulled outwards. It has a mass of 0.25 kilograms. We got a motion detector over here and a force sensor over here. So important things to remember: we release it from rest, it oscillates back and forth, and then that seems to be it. So we have a velocity versus time graph where I circled 2 points that we're going to use a little bit later, and then I shaded some areas over here and over here, which kind of faded a bit, but we're going to use those a little bit later as well. All right, so for part C, it says using the velocity versus time graph, calculate the change in kinetic energy of the cart from time equals 0.5 seconds to time equals 2 seconds. Show your steps and substitutions. So this one is pretty straightforward. I'm actually almost surprised how simple it is, but our delta K is the final minus initial, which is the kinetic at 2 seconds and 0.5 seconds. So at 2 seconds, it was 0, and at 0.5, it's 0.3 meters per second. So then I basically just plugged those in for my velocities, subtracted, and then you have a negative change in kinetic energy. For the second part, it says using the force time graph, estimate the change in momentum of the cart from 0.5 seconds to 2.5 seconds. Briefly explain how you arrived at your estimation. And it says estimate because the first thing I'm thinking of is change in momentum is impulse. And then when you do force times time, you're finding the impulse, which is the area between the curve and the x-axis. And since the line is curved, it's going to be hard to find that exact area. So from 0.5 to 2.5, I'm going to go ahead and look at it. So here's 0.5 to 2.5. Now I immediately notice that I have this portion underneath in the negative region, and then this portion over here that is basically the same thing in the positive region. So I'm already predicting that it's going to be about 0 because I'm going to have some negative value here that's going to match this positive value, and they're going to cancel each other out. So I'm just basically articulating that and then saying that the area between the curve and the x-axis is the impulse. The amount of area between 0.5 and 1.5 looks to be equal to the area between 1.5 to 2.5 seconds. Therefore, the delta P, or impulse, is about 0 kilogram meters per second, because from 0.5 to 1.5, that has a negative change in momentum, and 1.5 to 2.5 has a positive change in momentum. So that seems to be pretty clearly explained. Maybe not the best, but I think I got the point across. Now, do the data from the velocity versus time graph confirm your estimation from part C? Briefly explain. So I'm going to go ahead and look at the velocity from 0.5 to 2.5. So here's 0.5 to 2.5. So they're both at 0.3. So there is no change in velocity. So my delta P, my impulse, is mass times change in velocity. And if my change in velocity is 0, that means my impulse or change in momentum also has to be 0 because the mass doesn't change. And both velocities are 0.3, therefore the delta V is 0 meters per second. So maybe I need to add a little bit more there, but it did say briefly explain. And if there's no change in velocity, then there's no change in momentum in this particular case. And that does it for question number 2 of the FRQ section. So hopefully you did well on that. Thanks for watching and listening.